Hi, welcome to our first training session, where we will demonstrate how we can easily design, build, and test LPC 2148-based embedded system, which is capable of blinking LED. Embedded systems programming is quite different from regular programming on a PC. An embedded system comprises of both hardware and software component. Any embedded system project involves three important steps. The first step is to select the programming language, the second step is the selection of the microcontroller, and the last step involves identifying electronic components. C is a high-level, general-purpose programming language. Applications that generates codes to run on a PC is called regular C compiler, while PC-based application that generates code for a specific microcontroller is called embedded C cross-compiler. Programs written in C are readable and easy to debug. C programs have simple syntax and has only 32 keywords. To debug embedded C program on the PC, we use a simulator. We use a Jaguar debugger to download and test the program running on the target hardware. We will be downloading and installing a student version of Crossware ARM Development Suite. The Crossware toolchain includes C cross-compiler to generate code, linker to combine object files, simulator to create virtual ARM chip on PC, and debugger to download and run the program on the target. The most important part of our embedded system will be LPC 2148, which functions as the brain of the system. LPC 2148 is available in a small LQFP64 package. Each pin is multifunctional and can be programmed as input or output. Each of these I/O pins can be either digital or analog. ARM7 registers are 32 bits in size, and it can read or write 32 I/O pins in one cycle. In this demo board, I/O pins are terminated in group of 8 on a header. If our LED is connected to header 1, we use bit 0 to bit 7 of the 32-bit register. If we connect LED to header 2, then we use bit 8 to bit 15. If we connect LED to header 3, then we use bit 16 to bit 23. LPC supports crystal oscillator, up to 30 MHz, a 16 MHz oscillator, is wired to this demo board. A 5-volt dropout regulator provides 3.3 volt power to LPC 2148. A switch is connected to LPC 2148 reset pin number 57. A low on pin 57 causes processor to begin execution at address 0. The USB Jaguar debugger is used to download program from the PC to the target. One end connects to the PC USB port, while other end connects to the ARM 20-pin JTAG connector. Let us have a final bird's eye view of our demonstration board. LPC 2148 processor, header 1 for P0.0 to 7, header 2 for P0.8 to 15, header 3 for P0.16 to 23, 16 MHz crystal, 5 volts to 3.3 volt regulator, the reset switch, ARM 20-pin header for downloading software. Crossware Embedded Development Studio is a Windows-based application with all tools needed for developing embedded applications. The integrated development environment comprises of a code editor to write and edit your code, a project editor to view of all the files in your project, a cross-compiler that transforms your C program into machine-readable hex file, a debugger to test your program. If the debugger tests the code on the PC, then the IDE simulates the target processor on the PC. If the debugger has to run the code on your demo board, we require USB Jaguar debugger to connect the PC to the real processor. C is the mother of all programming languages. C supports both high-level programming and machine-friendly low-level programming. C is a portable language and hence, once the code is written, it can run on any computer or any embedded system. Before we start learning C language, we need to know how to give instructions to the computers to develop our program. We need to learn how the central processing unit works. If you open the CPU, we will find the following parts: The program memory, this is where our instruction lies. This area of memory is called read-only memory or ROM. The read-write memory, also called as RAM, where CPU stores information. A peripheral address space is a part of a microcontroller that interfaces with the outside world. The input-output device can be digital or analog. Peripheral space also includes timers, real-time clock, serial and USB port. The CPU operates at a speed of 16 MHz. It expects you to provide 16 million instructions every second. ARM7 has 16 general-purpose registers, R0 to R15. One of these registers can be used to point to any memory address, while the other can be used to read or write data from that location. Register R15 is called program counter and stores the address of the next instruction. Program counter is only used to read program instructions. All registers are 32-bit wide and can access 4 GB of memory. Let us now learn how 5 registers are used to configure and operate each peripheral pins. The first step is to select the pin function. Each pin can have a maximum of 4 functions. 2 bits in pin select register selects one of the 4 functions. On reset, pin select register is set to 0. This configures each peripheral pins to be general purpose I/O function. If the pin select register is set to 1, this pin function changes to serial transmit. If the pin select register is set to 2, this pin function changes to pulse width modulation output. Each general purpose I/O pins are controlled by 4 registers. If the bit in the I/O direction register is 0, then the corresponding pin is configured as input, and if the bit is 1, then the pin is configured as output. If the pin is output, then a 1 in I/O set register can set the output pin high, while a 1 in I/O clear register clear the output pin to low. The status of the I/O pin can be read by I/O pin register. 32 pins are grouped together to form P0 port. We have 2 port in LPC 2148, port 0 and port 1. Let us learn how to program ARM7 using embedded C. Programming is only manipulating data. Our aim is to use ARM7 CPU to send data to 8-bit LED array connected to general purpose I/O port, bit 0 through 7. Embedded C is a structured language in which a single program is divided into many modules called functions. The starting point for a C program is the function main. When the processor resets, the program counter, R15 is set to 0, processor start executing the startup code, located at address 0 in the ROM. The startup code clears the RAM data. And the startup code loads the program counter with the address of function main, and start executing the main function. The aim of our project is to make use of embedded C to toggle LED connected to the general purpose I/O port. Please note, all our peripherals are memory mapped. This would mean each register has a specific address. The question is, how do I point to a memory location in embedded C? A character variable is a name given to a memory location. It is capable of storing 8 bits of data in the memory, while an integer variable stores 32 bits or 4 bytes of data in memory. A pointer is a name given to a memory location which stores address of another memory location. Please note, all memory address are 32-bit long, hence any pointer pointing to character or pointing to an integer variable will requires 4 bytes of memory location to store it. Data pointers in C play an important role in embedded C. Let us now write a simple embedded C program which can read and write any location on the memory map. As usual, in every embedded C project, function main is the entry point. Let us create a new function, call RAM_write. This function is called from our main routine. The simple RAM_write function, using pointer, can now read and write to any RAM address. We create a character pointer, we point this to a location in RAM, we check the value of RAM. It has a value 0 before stepping, and 55, after we single step, our function. This means we can now access any location on the memory map using pointers. Embedded programming is simply manipulating data using pointers. The memory map address for pin select register is provided in the user manual. We can use this information. We know all ARM7 registers are 32-bit wide. Hence we create an integer pointer to access pin select register. It is very difficult to browse user manual for register information. Hence Crossware IDE provides a point-and-click wizard, which automatically create named pointers and associated code for each peripheral. When we set the I/O direction register to be output, the code wizard creates a configuration code for our use.